Hi, my name is Sohan Paul, and this is my Lab 4 for Physics 2, Magnetic Dipoles. The purpose of this field is to measure how the magnetic field produced by a small bar magnet changes with distance, and how to compare those measurements with the theoretical predictions derived from the Biot-Savart law, both for on-axis and off-axis magnetic dipoles. A small glimpse of our results shows that the net magnetic field, was around 7.17 teslas, and you can see the average distance and the average magnetic field for our on-axis measurements below that. To get the results I previewed earlier, we used two fundamental principles. One was the magnetic field from Biot-Savart law, which provided the magnetic field at a point in space due to a current carrying wire, as well as the magnetic field of a dipole. The system we were observing was the bar magnet and the magnetic field that it produced. The things that affected the system that were in the surroundings were the Earth's magnetic field and the smartphone that we were using for measurements. The lab process initially consisted of getting on-axis and off-axis measurements due to the bar magnets and magnetic field. This consisted of zeroing out either the magnetometer in the y-axis or the x-axis. As you can see, the first thing we did was to try getting different magnetic field values and assess the distance that we had to get from the bar magnet for each of those values. And you can plot the logarithm curve, the distance to the magnetic field, and it's roughly linear. The second main step in the lab process was to move the magnetometer of the phone far enough away from the bar magnet such that we got a net magnetic field of 100 teslas. We then moved it up by the same amount, dperp, and calculated the magnetic field in the x, y, and z coordinates, the y being corrected because the Earth's magnetic field was providing some magnetometer readings as well. Using the fundamental principle discussed earlier, where we were able to calculate the magnetic field of a dipole, we were able to calculate the dipole moment of that bar magnet. We then used this in our computational model and reconstructed a very similar experiment, getting the overall magnetic field in the different directions, as well as the net magnetic field as well. The magnitudes of the net magnetic field we calculated in our computational model and what we actually saw in the magnetometer readings were significantly different, and this could be due to several reasons. One being, the real magnet deviates from a perfect dipole. The magnetic domains and non-uniform magnetization could lead to field distortions that are not exactly of a perfect magnetic dipole. Additionally, we assumed when we calculated the magnetic moment an exact net magnetic field to distance relationship. However, this would actually in real life vary significantly with noise, as our measurement process was not perfect. We were estimating where the magnetometer was through tapes with not zero thickness. Finally, the smartphone magnetometer itself has calibration offsets, limited sensitivity, and background noise such as earth field and nearby metal that could significantly throw off readings. We now answer several what-if analysis questions. What if the experiment were not oriented to magnetic north? If the experiment was not properly aligned to compensate for Earth's magnetic north, the Earth magnetic field would add a vector component to the bar's magnetic field. Depending on the orientation, this could either increase or decrease the measured p-values in the x direction. As a result, the distance dependence plot of the natural log of the magnetic field to the natural log of the distance would show more scatter, and the relationship would not be as perfectly linear. The slope might deviate from the expected value of -3. What if the two identical magnets were combined end to end? Well then, the two identical magnets would create a total dipole moment which would effectively double, because the dipole field is proportional to the magnetic moment. So then the field strength would also double.